All right, so I want to start the work holding and tooling with, if it sounds funny, you should probably stop the machine and check. This was a 3/4 inch end mill that we're going to look at in here in a little bit, and it's buzzing along, making, just sounding nice, has a good tone to it, and all of a sudden the tone changes and the coolant starts spraying in a different direction, and it was just one of those, what's going on? All right, so hit feed hold, and the end mill has pulled this up. The end mill's right about there when I stop the machine and I pause it, and it is in the process of pulling this part up, and it has that much to hold on to before it goes flying out of the vise. All right, so um, what ended up happening is that when I checked this piece, ran the calipers across this end and this end, there was about a 10 thousandths difference. So the floating jaw of the vise will typically find its way around and still clamp for the most part. It's not the most rigid setup, but it would clamp. But in this case, it ended up pulling that up just enough, and that is managed to save that part. It was the roughing passes, so there was still material to take off. So even though it moved a little bit, it was a save. All right. Other times you're just going to hear the ka-tunk ka-tunk as it's bouncing around the end of the machine, and hopefully you didn't break a $90, $150, $200 tool. All right. So as you're going through and programming, I will throw out my mantra of, it's not a matter of if, it's when and how bad. You are responsible as the programmer to make good decisions and make sure that your setup people and your operator are a part of your communication loop. And I mentioned earlier that in most of and almost all my jobs, I've been all three. I program, I set up, and I operate. So if there's something wrong with the part, there's only one person to go to and say, "Why did you do that?" All right, and then it's it's about corrective actions at that point. What happened? Why did it happen? How can we fix it? All right. So if your operator or your setup guy comes to you as the programmer and says, "Hey, we got a problem with the machine," you take them serious and you go find out what's going on, because they're your eyes and ears, unless you want to be the one standing at the machine watching it run all of these parts. Okay. So work holding, standard CNC vise. A lot of these you will notice the little rust spots in Arizona, and I'm sure elsewhere with the hard water. You do not want to run hard water. All right, so in the 6 months or so that we transitioned from RO and I'll just put some hard water, the coolant is thick enough. No, it's not. I go through WD-40 and Scotch Brite like you wouldn't believe, cleaning up the accessories for the machine. So these are standard work stops. So either something that clamps to the vice jaw, or a bar that hangs off the side, or there's other little 5-axis things. Everybody has kind of their preference of work stops. And these are on the back left side. And that is my only explanation, my only reasoning is that most of your operators are going to be right-handed. So you have the vise handle in your left hand, you put the part into the vise with your right hand, bank it up against the stop, close the vise with the left hand. That's the ergonomics. There's nothing that says that you always have to put the stop at the back left. If it's more convenient or there's a reason to maintain a datum, so we machined something from this side and then I flipped it over and I have precision tolerances, or I have something that I need to hold on to, then I would switch the work coordinate, the work stop, from the left to the right. All right, so you're making those decisions as you go. What makes sense as you're stepping through the processes for generating these parts? So the 3600V, in this case the Kurt, or any of the CNC vices, these are ground on the bottom, the two sides, and the end. So if you're putting this on a tombstone, the end will sit on the lip and you can align it vertically. If you have an out of position where you want to put this on the side, and when I bore you with videos, home videos later, there are a couple where we put this on the side, we run the indicator across the bed to align it, and now I can hold on to an 8 or 9 inch tall part and have decent rigidity because this vise goes on its side. We also have what's called a floating pin stop, or what I call the floating pin stop. I've always heard it referred to that. So I went into the drill blank, reamer blank drawer and found the most oddball size that nobody will ever use, 11/32. All right, that was just my preference. So 344, 343.75 if you really want to take it out that far. But when I touch this off, I leave a little bit for the stock, and then I add 172 into the coordinate, and that's how I'm telling it where 0 is at, and to move over about 200 thousandths or so, so that when this comes down, it's written as a macro. So in the control, I will post out from MasterCam. I'll post out from my CAM program, and I will write in a call and say, go call program 1000, do this little tool change. So it goes and it gets tool 24, 25, whatever it is, brings it down, stops. I bank the material into the pin stop, and then when I hit cycle start, it retracts, goes and puts the tool away, and now I can run down both sides of the vise and have decent chance of cleaning up my material on both ends of the stock. All right, and then the standard work stop that goes into the T-slots on the table. I changed this out to a nice aluminum rod after I ran my carbide tooling over the steel one half a dozen times and started chipping tools and the vibration and everything. At least when you hit the aluminum, it just kind of bounces off and makes a horrible noise, but also don't have to worry too much about hitting it. So this is going to be adjustable and be able to stretch farther away from the vise, give you a little bit more room. One of the first production pieces that I ran, I thought, great, I'll throw 3 vices up on the table, I'll set 3 work offsets, I will jump from vise to vise, and the only thing I didn't think about, if you notice in this picture, these are D675 vices. And the designation on the D vices are, this is 6 inches on the jaw, and it opens 7.5 inches. So a 688, 6 inches on the jaw, opens up 8.8 inches. All right, the problem with 2 D675s and a 3600V is the 3600V is actually 15 or 5/16 of an inch taller. So my retract plane to a 1/2 inch and the first rapid move to the middle part scared me to death. So checking your heights, being aware of what the different vices, the issues, because you can look at this all day and until it makes that rapid move, you're not going to realize how close it is. And 5/16 is not kind of in that visual acuity. We'll talk about the subplates and the universal tooling plates a little later on. But this is a 2-inch piece of 7075. It has 998 holes in it. I built toe clamps as in my first machining position. We built just probably 100 of these little toe clamps, and the company gave me a set when I left, and so it was natural to put in quarter 20 tap holes and 1/4 inch dowel pins. So when we come up with probably one of the assignments will be to build a universal tooling plate or a fixture plate, and then we're going to position the part on top of it so that we can clamp and change clamps. So the only thing that I would have done differently instead of the 1/4 inch and 1/4 20s is gone up to maybe 5/16 or 3/8, because wherever these line up, I cannot put a screw in at the same line that I put in a pin. So I want the pin to be just a little oversized of my threaded holes. But it doesn't really matter what you do with the universal tooling plate or your universal fixtures. It will never hold everything that you want it to hold. It's a given that the first thing you put on it won't line up to anything. And you'll be digging out parallels, you'll be digging out spacers to reposition the items that you want to run. So just facts of reality. So this was a little part. This was actually programmed. So this would have been 2002, 2003. This was one of the first productions I mentioned. This was actually programmed in ProCam, and one of the last generations of ProCam. So I don't know if the picture didn't make it in here. But the main thing is that We've, before class, we talked about different softwares. What you're learning in in as far as going through parameters, learning in the way of processes applies to all of the CAM packages. So you should not be intimidated or shy away from any other CAM package that's out there. Now, Mastercam doesn't want me to say that because they want you to go buy Mastercam and work for people who buy Mastercam. But the reality is you're going to encounter lots of different CAM packages out there. And in the real world, you're going to identify strategies, techniques, figure out a process, make sure your posts are working, and start making parts. All right. There's only, I can't say that there's been any CAM package that I've walked up to that give me a week, give me 2 weeks, and a machine to run the code on. I will figure it out. Right. So you got to have that attitude that you're going to output code and you're going to be making good parts. So when necessary, we'll go to soft jaws. And so soft jaws are just blocks of aluminum that we put the socket head cap screws, and they just take the place of the hard jaws. The advantage of soft jaws is that we're going to be able to put in profiles. If I need to do a chamfer routine and it buzzes through the soft jaw, no big deal. No gain, no loss. These were for a little 4140 chromoly piece, and it was fairly hard material. The only downside is that after about, we ran, I want to say probably 100 at a time, is that when I didn't use the torque wrench and we'll talk about the torque wrench later on, when I was just tightening the handle by hand, I started deforming into the aluminum because the chromoly was that much harder and it was pushing the aluminum away. So probably about, well, I say 5 years, so that means 10 years ago I adopted the torque wrench. And every machine that I run has a torque wrench next to it, and I torque my parts between 15 and 25 foot-pounds. That means that the first part of the day in a production run has the same amount of pressure on it as the last part of the day. And if it starts throwing parts, then there's another issue. It's not because of the pressure. When you actually do the calculations for one of those vices, I think it works out to, if you get to 90 foot-pounds on either of those Kurt vices, it works out to something like 6,000 psi. You will bend your parts, and they will be throwing because they're bowed, not because they're coming loose. All right, so we'll talk more about that later. I have my own little soapbox about torque wrenches. So a miniature fixture plate, and actually that one's in my backpack if anybody wants to take a look at it. These are 440 screws with 1/8 inch dowel pins. So this is just a little baby vise. We had sensor brackets for a vacuum gripper, and it was basically for part present. And so this thing was only about 1.5 inches. And how do you hold on something that has no square edges? It's completely rounded, arced, everything else. And so throw up a piece of 1/8 inch, tape it to the table, run some clamps. If they kick off and make little weird shapes on the end, I don't care. I'm just going to take my 440 button heads and use them to clamp down my material. And then we go up to the 1/4 plate. So this is about 6 inches, actually 5.8, because the earlier vices that were actually 6 inches would not hold a 6-inch plate. So ended up cutting that down to about 200 thousandths under by about 8 inches. And you can see some of the patterns. That was an oval pattern. It's basically a sacrificial plate. I'm not worried about hitting the table. I'm not worried about hitting something that's, well, important. I'm going to take maybe 5 or 10 thousandths into this plate, and when I need it next time, I'm going to fly cut over the top of it, and it's a sacrificial plate. It's a consumable item to hold onto these parts. So when we do the toe clamp and have the pins for repeatability, if I get this set up, I'm going to get good repeatability from part to part. Stock is slightly oversized, and we're going to run around the outside for these oddball shapes. Now I may be changing clamps, swapping clamps front to back, side to side, but I have a means of holding on to something that is not normal or easily retained. So this part, I will bring in the fly cutter and the part. This is an example of what happens when you call tool 8, but tool 8 is a fly cutter, not a drill. And you have run it, and about the time you go, oh, that sounds funny, your fly cutter and your clamps and your part go flying out the side of the out the side of the vise. It's going to happen. All right, we want to minimize, and it's a matter of how fast can you hit that emergency stop. Never fast enough. So this is that bigger plate, and so when the vices come off, you can kind of see a big hex looking plate that we ran with the pins, and 2 pins across the back, 1 pin on the side. This is where I'm getting the repeatability. So when we talk about fixturing and datums, the plate itself becomes our primary datum. It has, well, hopefully it has 3 points of contact. If the material is pretty flat, then it's sitting down on the plate stable. And then we put 2 pins across the back or on the side. That's our secondary. And then the tertiary datum would be 1 pin to give us that 3rd point of reference to retain the parts. The choice that we're going to have to make on the programming side when we're doing this is, do I program at the stock and say that I have, I don't remember what this was, 10 by 9 piece of stock, and my part is going to live inside of it? Or do I program the part at the 0, 0, and at the control say step over 60 thousandths, step over 60 thousandths, and that positions the part in the stock? Yes?
What is it that you're making though for that particular part?
This was for a motor holder, electric AC motor for a conveyor system. So this had a couple of real tight bearing positions, and then this had kind of a weird offset angled rectangular shape. So it wasn't something that we could hold in the vise, and then it was also too big for the vise. So there's just anything that you would consider it's not naturally going to fit in the vise, and there's no other. We don't want to make a dedicated fixture for it. I'm running 50 of these, or I'm running 20 of these. So I can't really justify dedicating a fixture for it, but I have a tooling plate somewhere in the shop. I'm going to put it on that. So there's the little toe clamps in different styles. So these were Carlane and McMaster Car are pretty close, but Carlane is the tooling. So some of these are purchased and some of these are made. So it just depends on how much you're using. A lot of times I'll take a scrap piece of aluminum, a drop of aluminum, and I'll make clamps that I can run into, because I know that I'm going to be that close. I know that there's going to be a little buzzing sound, and I really don't want to hear the grindy, crunchy, sparky noises that go with it. All right, so try not to hit these, because these are D2 steel, heat treated to I don't know that they were much above 50, but they don't bend. They have good rigidity when I'm clamping down. So the heat treatment helps with the deformation and the clamping, but when you hit them, it's pretty dramatic. So we try not to hit any of these clamps. Different styles of Mighty Bites, and I want to say Mighty Bite was purchased by Destaco. So as far as brand names, I'm sure there's others that are pretty close, but these are kind of downforce. So you clamp the T-slot into the table, bring it up, and as you're tightening this set screw in the back, it's pushing down, and the little serrated edges are biting into your material. So you don't want to use that on a finished surface. But for rough stock, you're going to get it in position, be able to do a lot of interior type stuff. And the Mighty Bites come in, I want to say these were the 832s or 1032s. So it's only about a 3/8 diameter hex. And so for small fixturing and plates, these are going to give us decent clamping pressure and just minor deformation. And then the kit that most everybody's seen is the 1/2-13s with, I don't know, it's got to be about a 7/8 or 1 inch hex on it. So the way that these work is there's an eccentric. You can kind of see that this is turned off center and the hex is going through the middle. That as you tighten this down, it's pushing the hex about 60 thousandths. Right? So all of these clamps, the takeaway is that you can overcome these. If you get way aggressive on a cut, you will lift that part and throw it. So the people that hate mighty bites and the downfeed clamps did not back off from their normal feeds, really aggressive feeds and speeds, and the part came up on them. Right? So you got to be realistic that there is clamping force in this that will hold down. It will do a decent job of doing it, but don't let it get away from you. So when we talk about the Destacos, is pretty much an E4 link, and these were just some that I had around. So kind of the down, also a down. So as you pull down, or actually this one was a pull up. Yeah, this one was a pull up. So as this comes up, it forces it down, and that's providing the clamping pressure. When you push the lever down, this one's coming down and providing clamping pressure. This would be to locate into the fixture. So as it pushes down, the rod comes out and is pushing the material into your work stops. So those are pretty effective. If you have something that is pretty light duty, maybe a drilling operation that you don't want the parts vibrating, moving around, doing anything strange. These are great little fixtures, and they come in all different sizes. What I didn't put in here is the can't twist clamps, which also end up in the mix. And it just gives you something that the operator, if it's a repetitive motion, you're having to deal with any of those types of issues, that you can set it in place, clamp it quickly, do the operation, get it unclamped and out of the way. Standard angle plate, vertical 3-jaw. So at some point you needed to hold a round part in a vertical orientation. This one was purchased specifically for, but most of the time I look for the 6-inch or the 8-inch chucks that come off of a lathe and have kind of been disposed of for wear, because if you rebuild it and give it a little TLC, make some soft jaws, put some decent jaws on it, chances are you can revive it, attach it to an aluminum plate that mounts to your table or to the subplate, and now I have something that I can easily hold on to those larger round pieces in a vertical orientation, do machining on. And then the 5C Collet Closure. So this will mount in a horizontal position as a 4th axis. So my first 4th axis program was actually, I was the 4th axis rotating one of these, hoping that I didn't miss a count. And coming down real slow going, yeah, that's where that tool's supposed to go. But we had all the operations, we had all the clearances, and we ran a couple hundred parts with a spindle nose modification. So, an effective means of work holding and being able to, again, smaller diameters, but be able to hold round stock in a position. Probably the other comment is that even though the part that we mostly ran, I would set 3 of these up on the table, and it would take about 9 minutes. That same round part in a lathe would probably take a minute for all 3, because even with tool changes. But am I really going to go out and spend $60,000 and tool up for a turning center when I get this job once a year, and it's not really that cost effective? We're not seeing a return on investment that I need to make these in 2 minutes or 3 minutes per. So in that case, we make the vertical machining center work. Going into tooling, any questions on the work holding? So going into tooling, this little 3/4 inch, I want to say that's an OSG with a 10 coating, was the one that pulled up the part in the first picture. That was about a 90, just shy of $100 end mill. And it was running at 4,000 RPM at about 60 inches a minute. So when it changed tone, there was about 10 seconds to decide. From coming around the front and having that little vibration, and then coming around the side, that's what you get. most of the time you're going to push the emergency stop and watch whatever's going to happen. If you get lucky enough to hear it, stop it early enough, you'll save the tool, you'll save the part. Other than that, we always kind of talk about like I just mentioned on the turning center. You go out and you spend, as a company, $60,000 on a mill. You spend another $10,000 tooling it up, another $5,000 for software to run it efficiently. And by the time you hook the power up to it and put coolant in the tank and actually push the button, you're probably upwards of $100,000 just to turn the thing on, and you haven't bought material yet. All right, so all of the tools, tool holders, everything, doesn't matter how many you have, you could always use one more. It's part of the game. So when we talk about tool holding, if we switch back over, we'll pick that up. We have the ER32, and again, these get doused with WD-40 and the Scotch-Brite and get cleaned before they get put back together. So again, that hard water, use the RO water and invest in an RO unit or make the trip. It saves a lot on the rusting. Standard fixed holder. So this is going to take for a 3/8, it's going to take a 3/8 end mill. And there's always a little bit of a clearance issue. So where the ER32 and the ER16, and there's other sizes in between. So if a company happens to settle on 20s, you're going to see a lot of ER20s. Basically, it has to do with the range. So an ER32 will go from either 40 or 60 thousandths all the way up to 3/4 of an inch as its range of tool holding. Problem is, with a nut that is that large, there's some areas that a really small tool is not going to be able to get into. So we go to an ER16, which goes from 40 thousandths or so up to 10 millimeters or 3/8 of an inch. And with the smaller retaining nut, you're going to be able to get into more different geometry. The fixed holder then, where these two are going to have minimal amount of run out, probably less than a thou, generally about a half a thou, sometimes 2 or 3/10. All right, just depends. What's that?
What are you talking about on
the ER collets? Yeah, the fixed collet, and we were looking at the shrink to fit earlier. The fixed collet is typically going to have about a thou and a half, maybe 2 thousandths, because the set screw coming through the side, the size of the material, you're just offloading, you're loading the tool on in one direction for the most part. So we always know that we're going to have a little more harmonic. We're going to sacrifice some finish if we're going to try and do a finish tool with this holder, right? So I know that I can rough with one of these holders, and I'm going to have good rigidity. It's not going to move, but even so, we've had parts move and pull out of the ER32s just the same that I've had parts move and come out of the fixed holders. So it's, when you get aggressive, it's anybody's game. You want to increase your production and your feed rates, you're going to accept the risk that comes with it. Standard drill chucks, so the keyless, the baby keyless, and then the keyed chucks. One thing I've noticed, and it's one of those that's open for discussion because everybody has had different experience with keyless chucks. I don't like running the keyless chucks in my 10,000 RPM spindle. When that regenerative braking kicks in, I have seen these loosen. I have seen these loosen and drop a tool out. Right, so I don't do keyless chucks in the higher RPM spindles. The 4,000 RPM spindle doesn't bother. But because of the way the 10,000 and above, when it goes into that braking and it's reversing the torque, unless you really wrench on these with the spanner, and then you're also damaging the jaws and you're taking a $200 or $300 chuck, and every time you use it, you're doing a little more damage to it. I'll just go get a $150 keyed chuck that I know will not come loose, and I don't have to over torque it to get it to stay engaged. So again, personal preferences. Where I can, I'm going to put the drill bit in one of those ER16s or ER32s because then I don't have to worry about it. But we're always going to need something for the chucks. And then we always come up with the conversation of, well, do you put taps into your drill chucks? And then most everybody cringes and sure, no problem. I've had too many broken taps from putting them into drill chucks. They go into ER30 or go into the ER chuck. Yes.
Oh no, I was gonna say the only time you use those is when you're
Out of 30 out of the ERs.
well, yeah, you don't even really use those. The only time you use those is when you're like either edge finding or you're
Pretty much. That's a good point. That's what this one, after it dropped the first drill bit with like 6 parts on it. I have only used this for my coaxial indicator and my edge finding. And it's got excellent, it's an Albright chuck. It was a $300 chuck, so it has excellent run out. I mean, it's down for a drill chuck. It's well under 1,000. So I trust it to put my edge finder in and trust it for the coax. But where I can get away from the drill chucks, because every drill chuck that I inspected lately has had between 4 and about 12 thousandths of run out because the jaws are so just used up. So if you're not going to maintain them and purchase replacement jaws and treat it as a consumable, they're going to wear out and they're going to give you unpredictable results. So if you want a 1/4 inch hole that's actually a 1/4 of an inch, go over to one of the ERs. Fly cutting. So this is a B52. It's called a high-speed single point. And so they say this will spin at 6,000. I've spun it at 6,000 RPM with 60 thousandths engagement, and it is very impressive. Most of the time, to get that nice mirror finish in aluminum or decent finish in steel, it's about 1,200. So this is 5 inches in diameter. They come in 3 inch to 9 inch. And so I have the 3, the 5, and the 7. That gives me a good range for oddball sizes. And this will leave a mirror finish in aluminum. What I don't have in here are the multi-flute facing mills, but kind of the same thing. You have more flutes, but on occasion, chips are going to get underneath this, just like they're going to get underneath your multi-flute, and they're going to score the surface, and you're going to have those scratches from the machining process. The standard fly cutter for most manual is just the left-handed lathe tool in the holder, and you spin it and hope it stays balanced. They don't, I don't see them as often, but this is a 3/4 inch ski carb. It is specifically for aluminum, has a 45-degree helix, and it will cut 3 inch length of cut. It will cut 3/4 inch deep, 3/4 inch wide, 4,000 RPM at 40 inches a minute. And as long as it has good coolant, it will do it all day. And when we come back with the 3 inch length of cut, it will leave almost a mirror finish around the external of the part or on your bores. We've had customers ask us, why did you electroplate our aluminum parts? No, we hit the speeds and feeds just right on tooling, and we got to a 16 finish. Whether we meant to or not, that's where it ended up. I mentioned the OSG tin coating. The tin coating adds lubricity, so that's a whole nother conversation of when do you go with the bright finishes, the tin, titanium nitride. AccuPro is using zirconium nitride, which we've had really good luck with. Getting decent finishes, accelerated feed rates, all of those types of things. When do you go with Alten? Aluminum, titanium nitride, and then you get into, there's a range that you want for specific materials, and the exotic materials and going up into higher heat is coatings are going to help extend tool life. All right, and then quick standard 30-degree helix, a little extended length. So all of these are 3/8 inch end mills. So let's see which one of these. No, I guess no, it wasn't the stub. So standard length, extended length, the rougher, and then the ski version of it to where we have the aluminum. So you can see the difference between the 30-degree helix and the 45-degree helix as far as being able to eject a chip and get the chip clear, get the coolant to the cutting edge, and move the material. The high-speed steel rougher on the other hand, probably a manual machine. And the thing of note, center cutting, we're going to be able to plunge, center cutting, center drilled for grinding. We're not going to be able to plunge this end mill, or we're going to have to be at such a slight ramp angle that we're really not going to have much advantage. So when you use the roughers, it's usually for a specific purpose where you want to decrease, instead of one long stringy chip being cut on the peripheral of the end mill, we want to break that into about 20 smaller chips. And there are advantages in places where we would do that. So again, the ski carb, extended length neck down, and we got the tool geometry at the end. Also extended length ball, ball end mill, and the baby ball end mill, 1/8 of an inch with 4-inch length of cut. And in mold making, I have had that held on by about 1/2 inch in one of those ER 16s, and was 2.5 inches deep into a slot to make a rib. And then the lollipop cutter, or the 270 degrees of cut. All right, so when you kind of look at the end geometries, just different geometries for different purposes. And then thread milling. So on the larger thread profiles, rather than trying to drive a tap through some geometries, or even some of the larger pipe taps, I'm going to try and put a thread mill in, and the program goes into the hole and then circular interpolates a helix, so it cuts that profile coming out. It's a very accurate, a lot of times safer way of making geometry. It takes a little bit of setup, and it's a little disconcerting seeing that, again, $100 thread mill diving into the bottom of a hole and then slowly making its way up. Disadvantage is that if there's 30 turns, it has to make 30 turns. So it's going to take a little while, but I'm going to be able to hold a really tight tolerance, or a reasonably tight tolerance, based on the deflection of the part. The multi-flute thread mills are 2 to 3 times the cost, and they're specific to the pitch diameters that you're going to, or the pitch that you're going to run. So if I was running a 20 threads per inch, I could get a thread mill that had 10 teeth on it, and it would cut that profile in 1 or 2 circuits rather than 20 circuits. Right? It comes down to economies of scale of how much do you need and how bad do you need it. Profile cutters, so we have the roundovers, have a, let's see, concave, a couple of concave, and like oil ring grooves for different profiles. Slitting saws and T-slot cutters, right, different geometries. Sometimes in this case it was a jeweler's saw going into A2. So we're going to have a heat treated with these little gripper slots in it. And I didn't need much exposure in the saw, but I needed the rigidity. So this was only about a 32nd of thickness. And so we just go over to the lathe, make an arbor for it, turn everything on the center, get good run out for it, clamp the slitting saw in there, and go make a bunch of little cuts. Drill mills, right? We will talk about chamfering and the drill mills. I haven't ever used one of these as an end mill. The end mill profile could cut on the peripheral. Most of the time these are to make chamfers, occasionally a starter hole if it's convenient, and for the smaller ones I've even engraved with them. But these have excellent geometry for doing like a production deburr, something really complicated where I don't want to scratch it with my deburr knife or risk damaging the part. Then I'll write this into the program, and it'll take 5 or 10 thousandths off and touch every profile. And then sometimes you get weird callouts that have decent sized chamfers in there, and you just bury one of these and go. Drill geometries, and now I got to go back and look which one was which, but I want to say this was the parabolic, and this is a standard screw machine. When we talk about increasing feed rates, when we talk about more aggressive cutting, then we'll go to the parabolics. A standard screw machine length drill will probably do 1 times D if you're being aggressive going into the part. And the parabolic will do 3 to 5. So 3 to 5 times your diameter. So if this is a 1/2 inch end mill or a 1/2 inch drill bit, and I have the standard screw machine, I'm going to at most take a 1/2 inch depth of cut or a 1/2 inch peck. On the parabolic, I can push it 1.5 inches to 2 inches. I can pretty much bury this tool and it will eject the chip, and as long as it's cooling and not welding up, it's going to make a decent on size hole. All right, so again, parabolics, higher twist, slightly different in geometry. This was an aircraft extension, and then we went to the jobber length and then the screw machine. So kind of a good comparison of the jobber length with a standard helix and the parabolic with the tighter helix. Different types of taps. I should have zoomed in on that one a little bit more, or cropped it and blown it up, but we have the fast spirals. So bottoming fast spiral ejects the chips up. Doesn't mean that the chips are going to 100% clear. I've broken a couple of these because the chip hung at the top of the hole, not because it was packed up at the base of in the bottom of the hole. And then tin coated standard spiral point taps, and then roll form. And we'll talk about all of those and where you'd use those. And so roll form is also called an emboss or a thread forming tap. It doesn't actually cut a chip. It displaces the material, so it needs that larger tap drill so that it can create the thread. Form tools. So in this case was a 1/4 inch with a integrated countersink. So when I was drilling, it would go through the part. When I hit depth, it already had the edge break and the countersink on top of it. And then this was for a port profile. Can't even remember which project it was for, but we ran a dozen holes through, or ran it through a dozen holes. It reamed to size and put in the geometry for the pipe and for the pipe thread, and we were done. Oh, there's the lollipop cutter. So this will actually do undercuts and can basically go up on the interior of an undercut. Woodworking. If you get a hold of an odd looking end mill, in this case we have the standard down shear. All right, so most of the metal machining are going to have a down helix. This is a reverse up shear, and it is used in woodworking because you can still conventional mill. Make sure I'm getting this right. You can still conventional mill, but the tooling pressure is pushing the part down. Or climb mill, which would normally be pulling the part up away from your vacuum, from your fixtures, and the tool pressure is still pushing down even in climb. So then there is the up down. So the first 1/4, 3/8 of an inch. This is a 3/8 inch tool, so probably about the diameter, is an up shear, and then the remaining is the down shear. So it equalizes the tooling pressures. So if you're running again on a router that has vacuum and you're vibration or otherwise trying to pull the part off of the vacuum, this reasonably well equalizes those tooling forces so that you still get a decent finish and manage the parts. And then uniflutes, so 2 different uniflutes. This one's a brazed carbide and then this one is a solid carbide. And there is a close-up of the up-down. So I would recommend that if you run across one of these, put it back in the toolbox, label it whatever, but these are for wood. I would not run this in aluminum or try it in metals. And then the up shear, and that's just a strange looking tool. And then the uniflute, and then again the group of woodworking. And then the brad points. These still have the wax on the end of them, but there's a tip and then the flat. And again, it's so that you can go almost through the material but not break into the vacuum. And then it's with the wood geometry, it's going to clear and make a decent size bezel. All right, questions on the tooling? Yes.
I didn't see any through the tool cooling drills, which are the greatest things in the world.
I agree. If I had one, I would have a picture of it. So what I need to do is go out onto MSC and scarf their pictures and put them into my presentation. One of the things with through spindle coolant is it requires the higher pressure pump. It requires filtration. And so going the through spindle is, yes, you're going to be able to increase those depth to diameter ratios by quite a bit, or just plunge straight in because it's ejecting the chip back up the flutes as the coolant's coming through the tip. But it doesn't come without associated cost. So let's see, escape. All right, so we're running a little bit long. Let's do the speeds and feeds, and I'll explain the charts too, and then we'll call it good for tonight. Next week, get the demo versions of the software downloaded and installed if you're going to put it on your personal computers or laptops, and then we'll be into programming. All right, so at some point, I would hope that you've seen this formula. Sometimes it has a 12 times the cutting speed divided by pi times d. That's not the one you need to remember. Cutting speed times 4, because this is a best guess. I watched the Haas tutorial. I will put that up. They did the math, and it was 3.88. Okay, within my rounding error, I think I can live with 3.88, but I can't do 3.88 in my head. 4, I can pretty much do in my head. So when we talk about cutting speeds, we're, let me see if I can bump this up a little bit. Control plus. All right, not great, not bad, a little better. So when we talk about the super alloys, you're not going to be cutting those with high-speed steel, but that's our starting point. We're going to be able to calculate, and even some of the carbides, we're not going to make it much above those cutting speeds. Super alloys, titaniums, and a lot of the titanium grades are not going to run very much different than stainless. All right, different properties, some different tapping conditions, but very close to being that 20 to 100. Stainless at 50 is a good starting point. Tool steels, depending on the grade, 30 to 60. And we're basically taking these numbers and we're plugging them into the CS. For the diameters then, if we're running a 1/2 inch end mill, then 1/2 inch goes in there, 0.5. 1 inch end mill, then 1 inch. For turning, we're putting in the stock size. So that gives us a good starting point. And that's all we're looking for is a starting point, because after that, we're going to observe and react. If I can push that tool harder, I can override it and I can come up with actual feed rates and we can move into production rates. But the first pass through, I don't want to scare my setup guy, and I don't want to scare my operator to never want to run my programs again. I want them to be comfortable setting it up and then going, well, you can go a little faster. And I was like, oh, I know I can go a lot faster, but you guys are the ones that got to run it. All right, so carbide then is we take this number from the base calculation, multiply it by 3 to 5, look at your manufacturer recommendations. Some of the coatings and some of the tool grades and geometries are going to go up to 7, 8, and get really aggressive. The other one then is the inches per minute, our feed rate, goes into the RPM that we've determined up here, times the number of teeth on our tool, and then the chip load per tooth. So general rule, maybe 1/2 thousandth, depending on how it works out if it's a smaller tool, but 1,000 to 5 thousandths for finishing, 2 to 15 thousandths for roughing. 15 thousandths is a really aggressive cut. Most of the time I end up about 7 or 8 for a standard 1/2 inch end mill and decent amount of RPM. Reaming, standard rule is half the speed, twice the feed. So we calculate all this out. I cut the speed in half because I want that reamer to do more rubbing than cutting. And I want it to go in, out, be loaded, lots of coolant. And then I want to say this was a machinery's handbook, but life of the cutting tool is most affected by the cutting speed, then by the feed rate, and then least of all by the depth of cut. All right, so that's where the trochoidal, the high-speed machining comes in, is that we can take smaller bites of material, run at elevated feed rates, and still have a distinct advantage in getting that material removed and cleared out of the part. Let's save threads for another discussion, but I would say look through this. And I think I got most everything on this. So this video will go up on YouTube probably tonight if you need to review it. Or we get 2 or 3 weeks into the semester and you go, okay, where did you pull these numbers from? Be able to come back and pick up the video.